The Fermi paradox is this. We know that we live in a big old galaxy, in a big old universe. And let's, for the purposes of this discussion, confine ourselves to the Milky Way galaxy. The Milky Way galaxy, we now know, has something like 400 billion suns. And we now know that most of those suns have planetary systems around them. So trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermi paradox, at its heart, is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox. And I think it's a very good question. It's an extremely good question. And there can be many answers. And the great fun, or the great, I would say the intellectual value of the Fermi paradox. So if we accept that we haven't seen any, so let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement, so we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So one answer to the Fermi paradox, is the idea that we don't seem to see anyone, is that no one ever evolved. Right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 4.5 billion years old. So we know, as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago. But it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization. 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. If you think about it, that's a big ask. What I'm saying is, on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to erase, destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened. We know that there have been impacts on the Earth, right? We know that the famous impact that wiped out the large dinosaurs, there's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say, it's a property of a solar system. It's not really just a property of the planet. It's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life for 4 billion years, perhaps not. When we talk about rare earth, I think I would like to talk about rare solar system. Another possibility with the Fermi paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there and they are present in the solar system. It's possible. Let's think, for example, what such an intelligence might look like. Well, who knows? They could have sent nano machines to our solar system. There could be probes all over the place in the solar system, but if they're the size of an iPhone, then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it and we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi paradox is just that the galaxy is so big. The distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Well, perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. That's a possibility. One of the arguments against that for me is the argument, it's called the space travel argument against the existence of extraterrestrial life. And it's often framed in terms of self-replicating machines, so-called von Neumann machines. So imagine it's possible for us, for a civilization, to build a machine, some kind of AI, that's sufficiently smart and capable that it can fly to a nearby solar system, reproduce itself, copy itself, and then send the copy out to the next solar system, and so on. So you have, if you build a one successful replicator, you have an exponentiation of replicators. You have 1, and then 2, and then 4, and then 8, and so on, exponential growth. And you can show that even given our rocketry technology, you can cover a galaxy like the Milky Way in a reasonably short space of time. By reasonably short, I might even mean 100 million years. Right, that's reasonably short on galactic timescales. But the key point is once a single successful replicator has been launched, then it is inevitable that over a few tens of millions of years, the galaxy will be covered with replicators, and we don't see any evidence of them. It's possible that we can infer that if we assume that we could detect them, then the absence of them may allow us to infer that no civilization has ever got to that point. And I think that's quite a persuasive argument. Now, it's possible that there are many civilizations out there, but the advanced civilizations choose to remain hidden. Sometimes called the dark forest hypothesis, the quarantine hypothesis. We've been asked to make moral judgments or judgments on how a civilization will behave, what they will choose to do, and that's of course impossible to judge. But let's imagine civilizations, when they get technologically advanced, also get intellectually and morally advanced. And let's say that they choose, perhaps for good reason, let's say they choose to remain hidden because they don't want to draw attention to themselves. Let's say it's inevitable that if you think about it carefully and you think there are other advanced civilizations out there, then you choose to remain silent. You hide yourself as best you can. It's possible that that's the way that a civilization would think. Maybe that's the logical thing to do. I find it difficult to believe, given human history, that that's the way that intelligent civilizations behave. We certainly haven't made any attempt to remain hidden. so far. We've broadcast radio signals out to the stars, the Arecibo message, for example, albeit weak ones. We've launched on our space probes, like Voyager, maps, pulsar maps in that case, which shows the location of our solar system should any other civilization find it. So at least at the moment, we haven't come to the view, which may be a wise view, but we haven't got there, that we should remain silent. Quite the opposite. We've tried at every opportunity to broadcast our existence. Maybe that's because Carl Sagan argued, I think, that a sufficiently advanced civilization, a civilization that can build interstellar spacecraft and communicate across interstellar distances, perhaps is wise enough to have overcome those primitive instincts, the instinct to cause trouble, to fight wars, to colonize, to walk over other civilizations. Perhaps it's inevitable that with technological advance ultimately comes wisdom. But it's a hypothesis. Maybe it is. Maybe it's just anybody sufficiently clever to build an interstellar spaceship will be also sufficiently clever to hide it and not draw attention to themselves. Maybe it's immoral, maybe it's like Star Trek. Maybe it's the prime directive. Maybe it's morally certain that if you're sufficiently advanced, you decide to take the position that you will never introduce yourself or interfere with another civilization. Maybe that becomes a kind of law of nature for sufficiently intelligent beings. Maybe that's conceivable as well. Another explanation for the Fermi paradox might be that civilizations live and die. They rise and then they fall. And because of the sheer timescales involved and the sheer size of the galaxy, no two civilizations ever overlap. I once had the great pleasure of meeting Frank Drake, the Drake equation, a legend, in his house. And he also grows orchids. And I arrived at his house just coincidentally on the day that this rare orchid flowers. And it flowers for, I think, 1 or 2 days and then goes away again for the year and then flowers again the next year for 1 or 2 days. And he used it as an analogy. He said, well, maybe civilizations are like that. So maybe civilizations are like rare orchids, and so they flower and die and flower and die. And just because of the sheer timescales involved, none of them ever overlap. And so there could be the wreckage, the ashes, the fossils of civilizations out there. But of course, we would have no way of knowing until we explore the galaxy and maybe find the ruins of these other civilizations. Who knows? I mean, it's quite plausible if you think about it. Are we going to exist in 10,000 years' time? It's, to a large extent, in our hands. Maybe we're sufficiently stupid that we won't exist beyond the next century. There's an idea in this field, trying to explain the Fermi paradox, called the Great Filter. Now, the Great Filter can lie in our future or our past. So let's think about what it would mean for a great filter to lie in our future. That would mean that civilizations do arise in the Milky Way galaxy and get to somewhere like the position that we're at now. So they develop rocketry, they develop nuclear power, nuclear weapons, for example, they industrialize, but then there's a filter in the future that stops them becoming true spacefaring civilizations. So stops them becoming multiplanetary species and stops them ultimately traveling between solar systems to begin to colonize a galaxy. So why might that be? Why might there be a filter waiting for us in our not too distant future that's going to stop us going onto Mars and stop us escaping our solar system? What might stop us from becoming an interplanetary species and ultimately traveling out beyond our solar system? I don't think it's technology. As far as I can see, I don't see anything in the laws of nature in principle that would stop us from becoming an interstellar species. Might be 1,000 years in the future, 10,000 years in the future, might be 100,000 years in the future. Even that, right, 100,000 years, it's a blink of an eye in the lifetime of the universe, in the lifetime of a galaxy. So I don't see any reason in principle why we couldn't become an interplanetary, interstellar species other than potentially our own stupidity. And I think that probably it could be one of the reasons why we don't see any other civilizations around. It could be that our knowledge, our scientific prowess exceeds our wisdom, exceeds our political skill. It could be that once a civilization develops the means to destroy itself in the form, for example, of nuclear weapons or biological weapons, or maybe some kind of a lack of control of AI, who knows? It may be that once a civilization acquires that technical know-how, then it goes ahead and destroys itself essentially inexorably, because it's just too difficult politically to run a civilization that has the power to destroy itself. If you look back through our recent history, there have been several occasions that we know about, that I know about, and you know about, where we came very close to destroying ourselves, or at least setting us back to the Stone Age, basically. The Cuban Missile Crisis, well-documented events in the 1980s, for example, where there could have been nuclear launches and weren't, and I'm sure there are many others that we don't know about. There's the challenge of climate change. We're completely incapable of coming together at the moment as a global civilization to address that challenge. That could set our civilization back. Biological weapons, the threat of AI, we seem to be completely incapable of regulating those threats. So it might just be almost a law of nature. Things like us, right? Things that can build an industrial civilization are just inherently too stupid to get out there to the stars, and I wouldn't put that past us. My favourite's the other one, so I'll do the other great filter. If I was to guess, and this is a guess, right? If I was to guess why we see no evidence of other civilizations out there, the so-called Great Silence is what astronomers call it, is because there aren't any, and there never have been any. That's my guess. The reason I guess that, and I emphasize it's a guess, is biology. So if you look at the history of life on Earth, then we see that life began 3.8 billion years ago, let's say. But then we see for the best part of 3 billion years on this planet that there's nothing more complex than a single cell. 3 billion years. It's only in the last billion years or so, perhaps a little bit less, that multicellular life has existed on this planet. And there could be good biological reasons for that. One that springs to mind is the evolution of what's called the eukaryotic cell, which is the cell with the cell nucleus and all little organelles and chloroplasts in plants and all those things, which form all multicellular living things on the planet. Those cells, which seem to be prerequisite for complex multicellular life, evolved once on this planet, as far as we can tell. It's pretty widely accepted. It's called the fateful encounter hypothesis. And so it seems that there was a very unusual evolutionary event at some point, maybe a billion and a half, even 2 billion years ago, that laid the foundations for us. If that's typical, if it typically is the case that it takes 4 billion years from cell to civilization, then I think there may be very few planets in a typical galaxy which are stable enough for long enough for that process to proceed. And we could be, for all we know, on the fortunate end of evolutionary timescales. We don't know. Let's imagine that actually we were on the lucky side, and really, on a typical planet, if there is such a thing, then it takes 3 or 4 times as long. That would exceed the current age of the universe. My guess is that whilst I think there might be microbes all over the place, I wouldn't be surprised, I'd be delighted, but I wouldn't be surprised if we found evidence of microbes on Mars, Europa, Enceladus, even in the subsurface oceans of places potentially even as far out as Pluto, right, in subsurface lakes, if they exist, liquid water below the surface, who knows? I wouldn't be surprised if we find microbes all over the place. But a galaxy full of complex living things, other planets with not only complex life, but sentient life, things as smart as us, things smart enough to build rockets and head out to the stars. My guess is that a typical galaxy may have less than, on average, less than 1 civilization per galaxy. Let's put it that way. And actually, just to say, there's a very famous book I'd strongly recommend, Barrow and Tipler, called The Anthropic Cosmological Principle. It's a great book, one of the books I grew up with. And in that book, Barrow and Tipler say that in their view, there might be 1 civilization in the observable universe. which should be us, right? So who knows whether we should go that far. But I think civilizations are very rare. Okay, now we walk outside and over Westminster, there's a spaceship hovering. I wouldn't be in the least bit surprised. I mean, there are deep questions. It's also interesting because then we get a profound puzzle about why there don't seem to be many civilizations around. If we don't find a way of not compromising, but understanding that the world is very complicated. So then it's not only a single country, it's all the different countries with different cultures and different political histories and different views. If we don't find a way of sort of stopping arguing and trying to find a way to make that work, I've just given everyone the means to destroy themselves. Well, one point is that it's expanding and we always see the same radiation out there, so the glow of the Big Bang. But there are some deeper reasons. The one from the theory of inflation, the best way to explain the universe, the properties that we see, is that it's very much bigger than the piece we can see. So, for example, we measure space to be what's called flat. I don't even have to say what's called flat. It is flat. So if you imagine slices of space, let's imagine slices of them at different times. So you just slice the universe and say there's a big sheet. It's like this table.
Okay, like a table.
There's a sheet of space, and there's another sheet, another sheet. And it can have a geometry, right? It can be flat like a tabletop, or it could be curved like a sphere, or it could be curved in the opposite direction, sort of like a saddle or a bowl. And we can measure that. And when we measure it, we see it's absolutely flat. And that's a very unusual thing for it to be like. It requires, because what Einstein's theory says is that the shape of space, that the curvature of space is determined by the stuff that's in it. That's basically Einstein's theory of general relativity. Put stuff in space and it curves it and bends it and warps it and stretches it and so on. And what we find is that there's precisely the right amount of stuff in the universe to have a completely flat universe. And the explanation, the most favoured explanation for that, is the universe is way bigger than the piece we can see. And so it's like looking at a piece of the Earth. If you look at a little 1 mile square of the Earth, right, then it's flat, right? You have to look at big distances, kind of order the radius of the Earth, or not, bigger than 1 kilometre anyway, or 1 mile, to see that actually you're on a curved surface. And that's one of the ideas about the universe and why it appears to be the way that it is, because it's way, way bigger. So we're just looking at a little piece, and that's why it looks flat. And that's the best way to think about it is not to think of 3 dimensions of space, because then we can't picture it.
Okay.
But you can think of 2, like this tabletop, and that's all right. We just forget the other one for now. And so you know what flat is on this table. I mean, you could define it. So you could say, for example, that if I draw a triangle on the top of the table, then all the angles add up to 180 degrees. So that actually defines flat. If you did that on the surface of the Earth with a big triangle, then the angles wouldn't add up to 180 degrees. Or you could draw a circle and say, what's pi? So pi is the ratio of the circumference of a circle to its diameter. That's only true on a flat surface. It's different if the surface is curved. So you can define flatness. Oh yeah, there's a 3rd dimension of space,
right.
But the same applies. It's just a generalization of geometry then. So you can the point is we can picture it in 2 dimensions, but you can draw. You can quite literally, you could imagine sending light beams out, and we do this measurement actually. We can look at the most distant light we can see, which is something called the cosmic microwave background radiation, which is if you imagine looking out. If you look at the Andromeda Galaxy, which we can see with the naked eye here in LA, you can see that. It's the most distant object you can see with the naked eye. And it's about 2 million light years away or so, which means the light took 2 million years to get to us. So it's a long way away, but it's very big. So as you look further out into the universe to more and more distant galaxies, you're looking further back in time. Because you look at something that's 1 billion light years away, then the light took 1 billion years to get to us. So you see it as it was 1 billion years in the past. And we can actually look so far out that we can see almost back to 13.8 billion years ago, which is very close to the Big Bang. So we can look to light that began its journey before there were galaxies.
And that's the oldest light in the universe, which is, by the way, one of the pieces of evidence when people say, I don't believe in the Big Bang. The answer is, well, you can see it. So it's just there. You can see it. We have pictures of it. That light, it turns out that there are sort of structures or ripples in that light, which we can use as a ruler. So quite literally, as a ruler on the sky. And then because that light's been travelling through the universe, we can see how that ruler has been distorted as the light has travelled through space. And so we can infer whether space is flat or curved, or how it's warps, if you like, just from that measurement.
So quantum mechanics is the base theory, we think. I think people tend to think of quantum mechanics as something that applies to atoms and electrons and particles, but not to us. And that's not right. So quantum mechanics is the theory that describes everything. The point is, though, it produces, when you look at big things, it produces behaviour which can be more accurately, or more usefully, not more accurately, but more usefully described by things like Newton's laws. It is necessary to understand quantum mechanics to understand how a transistor works, for example, or how a laser works, or how, of course, a nuclear reactor works, or the sun works. So it's not just a theory that's a theory of little things bouncing around. It's a theory that's necessary to understand a lot of things that we take for granted today. And it's an unusual theory. It's strange because it's got probabilities in it. And it was Ernest Rutherford, actually, so famously got the Nobel Prize at Manchester for discovering the atomic nucleus. But he pointed out that in the late 1800s, early 1900s, when we start looking at radioactivity, you see that radioactive decay is a probabilistic process. So it means that given something like a uranium nucleus, you can't tell, even if you made 100 uranium nuclei at the same time, you could just make them, then you can't predict when any one of them is going to decay away and emit some radiation. Basically, it's probabilistic. And so that idea was shocking to people, that it appears that the world is not like Newtonian clockwork. So I would say quantum mechanics, my explanation is it's a weird theory, it's a kind of probability theory, and but it's the way that things actually are. So you can give the numbers. So the nearest large galaxy, Andromeda, is about 2 million light years away, which means light travelling at 300,000 kilometres per second. From our point of view, takes 2 million years to travel from the Andromeda galaxy to us. So if you go away from the city lights and out on a clear sky, and when there's no moon particularly, then you'll be able to see Andromeda if you've got some binoculars, and it's worth looking at, because the light entering your eye began its journey 2 million years ago, which is before we'd evolved on Earth. So that gives you a sense, and you can see that. You can just about see it with the naked eye, because it's big. It's a big galaxy, about 1 trillion stars. And it's actually, although it's very faint, it's bigger than a full moon on the sky, so it's a big thing. I think that's the best explanation of the scale, because you can just about, I think, get your head around that. But that's the nearest galaxy. So when you start talking about galaxies that we see, beautiful images with the Hubble Space Telescope or the JWST, for example, you're looking at things that are 50 million light years away, 300 million light years away for a thing called Stephan's Quintet and onwards. And those, 300 million light years. And many of the galaxies we can see in photographs with like the James Webb, for example, those things are so far away that the light began its journey before the Earth had formed. And that's incomprehensible, I think. So the answer is I can't explain the true scale of the universe or picture it. And as we speak, we have several missions out there, but one of them is called Perseverance, which is a rover. And as we're speaking now, it's on the surface of Mars. It's taking samples. It's taken a lot of samples below the ground, and they're being packaged up for return to Earth in something that's called Mars Sample Return, because we think that it's possible that life existed on Mars or may still exist, because the conditions were right. It's certainly true that 4 billion years ago, almost certainly Mars was it's like Earth. When life began on Earth, Mars was pretty much the same, with oceans and an atmosphere and so on. So it's entirely possible. And it would almost be surprising if it hadn't existed, because then it would tell us that even given the right conditions, then maybe there isn't a high probability that life begins or geology becomes biology or whatever the origin of life is. So it does, in the sense that, so it's been done with photons, for example, so particles of light. So you can do the experiment where you essentially, it's based on having two photons that are entangled, quantum entangled together. So the best way to describe that in about a second is that they behave as a single system, basically, but you can separate them. And then you can arrange for another one to come in, so it kind of interacts with this one, such that it ends up, this one over here, which could be a light year over there, ends up being in the same photon, essentially, as the one that came in, or in the same quantum state. So it's teleportation. And the incoming one gets destroyed in that process, or its state is changed. So yes, we do quantum teleportation in the lab, so it's real. The question then becomes, how big an object can you teleport? And I think in principle, there's no reason why you can't teleport anything, right? But it's very much in principle. So no, the first time they came into physics was in 1930, I think it's 1935, in a paper by Einstein and Rosen. So they noticed that the description of the distortion of space-time in the vicinity of a star, which was discovered by Karl Schwarzschild in 1916, they discovered that if you take that description and you allow the star to collapse essentially into a black hole, and then you extend it infinitely into the past. So you say, well, let's imagine this black hole had always existed. So this universe in which this thing exists is an eternal universe. Then you get a wormhole. So a wormhole, the description of it is in the mathematics that Karl Schwarzschild discovered in 1916 for the distortion of space-time around a star. Literally, you have two universes, and they're linked by a wormhole. So one of them is a black hole and the other bit is a white hole. So that's just formally in the mathematics. So that's what a wormhole is in Einstein's theory. That requires this black hole to have existed forever. So, and by the way, if the black hole's spinning, then you kind of get an infinite tower of wormholes. So the so-called Kerr black hole, this was discovered in the 1960s by Roy Kerr for a spinning black hole. The solution to that, if it's this eternal solution, is that you have an infinite number of universes connected inside the black hole by an infinite number of wormholes. So the modern work on trying to understand what happens to things that fall into black holes might suggest that there's a kind of a wormhole that connects the interior of the black hole to the exterior universe. And so the singularity looks like this kind of network, tangled web of wormholes of some description. I hedge my language because the language isn't really known yet, but it's one of the ideas, one of the possibilities suggested by the mathematics for the interior of a black hole. And the other thing, the final thing to say, is that you might have heard about there's something called ER equals EPR. So it's Einstein-Rosen, which is wormholes, equals EPR, which is Einstein-Podolsky and Rosen. And EPR was a question about quantum mechanics and what Einstein calls spooky action at a distance, where you can have entangled quantum particles, and somehow it seems that if you do something to this one, then there's in a very real sense, this one's affected by it, but not in a way that you can transmit information, but it's quantum entanglement. And there is a picture where you can picture that as the two particles being connected by wormholes, and that was suggested by Leonard Susskind and others a few years ago. So that's called ER equals EPR. So wormholes are on the agenda in trying to understand what space and time are and how they behave. So they're not just science fiction. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating. They're odd things. The simplest way to describe a black hole would be a region of space from which even light can't escape. Predictions that such objects existed go all the way back to the beginnings of relativity back at the turn of the 20th century. But actually, really, I would say into the 1960s, perhaps even into the 1980s, many physicists felt that because of the intellectual challenges that these predicted objects pose, many physicists felt that maybe nature would not create them. I even saw that the great physicist Steven Weinberg say that he, in some sense, hopes that these things would not exist, because they're so confusing. But we now know that they do exist, and so we have to face the challenges that they pose. Black holes are interesting because, going back to the work of Stephen Hawking in the 1970s, it turns out that they demand that we think about both quantum theory and general relativity together. And the quest to unify those two great pillars of 20th and 21st century physics into what's often referred to as a quantum theory of gravity is in some sense a holy grail for theoretical physicists. But the problem has always been, well, is there anywhere in nature that we can look to observe something that requires us to merge those two theories together? And black holes really are the unique place, as far as we can tell, in nature, where we can see a thing just sitting there in the sky that demands that we consider those two theories working together to hopefully reveal a deeper theory. The idea of black holes goes back a long way, actually, back into the 1780s and 1790s. There were two physicists, mathematicians, natural philosophers, whatever you want to call them, working at the time, that had the same idea apparently independently of each other. One was a clergyman, an English clergyman called Mitchell, and the other was the great French mathematician Laplace. And they were both thinking in terms of an idea called escape velocity. So the escape velocity is the speed you have to travel to completely escape the gravitational pull of something, a planet or a star. For the Earth, for example, the escape velocity from the surface of the Earth is around 8 miles a second, 11 kilometers a second. If you go bigger, you make a bigger, more massive thing, let's go up to a star, for example, like the Sun, then the escape velocity increases because the gravitational pull at the surface increases. And actually for the Sun, it's somewhere in the region of 400 miles a second. It's really fast. What Mitchell and Laplace thought, and I think it's a very beautiful idea, is they imagined in their mind's eye, well, can you go bigger? Can you imagine more and more massive stars, giant stars, such that the gravitational pull is so large at the surface that the escape velocity exceeds the speed of light? And then you wouldn't be able to see them. There's a wonderful quote, actually, in Laplace's paper, where he says that the largest objects in the universe may go unseen by reason of their magnitude. And this is back in the 1780s or 1790s. So he's imagining stars where the gravitational pull is so vast that even light can't escape and you couldn't see it. Dark stars, I think he referred to them as. Now we know that such objects do not exist in the universe in that sense, in the sense that Mitchell and Laplace meant. But actually, they missed something, which is not surprising because it sounds almost paradoxical. But you can also increase the escape velocity, the surface of an object, by squashing it. And it turns out that if you take the Earth and you squash it down and squash it down and squash it down until it's about that big, the radius just less than a centimetre, then the gravitational pull at the surface would be so great that light couldn't escape. And that is essentially the modern concept of a black hole. Now, Mitchell and Laplace's calculations or imaginings were based on Newtonian physics, so pre-Einstein. We come forward to 1915, Einstein published his general theory of relativity, which is a different model, a better theory of gravity. And it turns out that black holes also exist in general relativity. Now, if we come forward to 1915, Newton's theory of gravity is replaced by a better model, a better theory, which is Einstein's general theory of relativity. But the idea that there can be objects that can be compressed such that they trap light is also present in Einstein's theory. The first physicist to predict such a thing, or at least derive the mathematics that describes such a thing as a black hole, although he didn't know that they existed, was a man called Karl Schwarzschild. What Schwarzschild did was provide an exact solution to Einstein's equations that describes space and time, the distortion of space and time, in the region of a star or at least an idealized star, which is a perfectly spherical, non-spinning ball of matter. It's a model, a simple model of a star. Now, Schwarzschild described or discovered the solutions to Einstein's equations that describes what happens to space-time outside such a thing way back, actually 1916, just after the theory was published. What Schwarzschild's solution also describes, though, although he didn't think in these terms at the time, was what that space looks like if you completely remove the star, but leave its imprint in the fabric of the universe behind. And that is essentially the theoretical description or the model of a modern relativistic black hole. Now, while Schwarzschild's solution, and by solution I mean we're to picture a distortion in space and time, a distortion in the fabric of the universe. While Schwarzschild's solution does indeed describe the simplest possible black hole that we can model in the universe, people didn't really think in those terms at all until later. You see in the 1930s, Einstein and a colleague of his, Rosen, for example, exploring that space-time and building models of what that space-time might look like. But I think it's true to say that really, certainly until the late 1930s, and actually arguably post-war until the 1960s, most physicists thought that such things would not exist in nature. So they were theoretically interesting, perhaps not practically interesting. The reason is that you have to create such a thing. So it's one thing to have a model of space and time that describes this object called a black hole, from which not even light can escape. But it's another thing for nature to actually make it. So if you go through the 1930s, there's a lot of papers. Actually, Robert Oppenheimer and a student of his, Snyder, wrote a very famous paper just before the war, which explored whether a real star in the universe, at the end of its life, could collapse and collapse without limit to form this geometry, this thing that we call a black hole. Just before the war, Oppenheimer and Snyder showed that under certain assumptions, a star could behave in such a way. But it wasn't really until the work of people like Roger Penrose and Stephen Hawking and several others in the 1960s that it really began to look as if nature would build these things. There's this great quote I remember with some fondness, actually. Arthur Eddington, a colleague of Einstein's, who was very English, very proper physicist. And he said, "Nature will prevent such absurdities from existing." Just, that's it. Nature will prevent it. Well, it turns out nature doesn't prevent it. We now know, and we've observed them, that stars do collapse to form black holes. And then theoretical physics moves on. So people accept that these things should exist, although it's true to say that we haven't actually imaged one until the 21st century. But in any case, people accepted these things should exist. More and more evidence mounted that they do exist at the centres of galaxies and at the sites of collapsed stars. But then we have to face the consequences. What does it mean for our understanding of the universe if there are these objects where space and time behave in a very strange way, where light is trapped, and where it would seem that anything that falls in is at the very least locked away from the universe forever? So to understand the conceptual problems that are faced if these things exist, then it might be worth just describing very briefly the Einsteinian description, the pure description in general relativity. A black hole, what do you see from the outside? Well, there's an event horizon surrounding the black hole. In some sense, it defines the boundary between the external universe and the interior of the black hole. The event horizon is very simply and a bit hand-wavingly, but it's a reasonable description. It's just, if you can imagine a sphere in space, and if you go across the boundary into the interior of this sphere, then even if you can travel as fast as the speed of light, you can't escape. So the event horizon separates the interior of the black hole from the external universe. We'll see a bit later why that's a bit of a hand-wavy description. But another description of the event horizon, which confused people all the way through the history of black hole research actually, certainly to the early papers in the 1930s and perhaps even post-war, was the idea that the event horizon, when viewed from the outside, is a place in space where time stops. And that's a direct prediction of Einstein's theory of relativity from the external perspective. If you watched, for example, an astronaut falling in towards a black hole, then from your external perspective, you'd see their time pass more slowly, slower and slower and slower, as the astronaut approached the black hole, until on the horizon you would see their time stop. That suggested to many people in the early days that a star couldn't collapse to form a black hole. It confused them. They thought, well, if a star's collapsing, then does it not freeze forever in some sense on the horizon? So all sorts of initial early conceptual problems, which ultimately were solved. The thing about relativity, just the one sentence thing to understand, is that time can stop from one perspective, but time can pass at the usual rate from another perspective. And indeed, from the perspective of an astronaut falling into a black hole, then for a sufficiently large black hole, like the ones that we find at the centres of galaxies, the astronaut would notice nothing at all as they fell across the horizon into the interior of the black hole. So time passes at 1 second per second on the watch of an astronaut falling in, but from the external perspective, time freezes on the horizon. So black holes are full of these apparent conceptual challenges, which are actually not conceptual challenges at all. They're just a central part of Einstein's general theory of relativity. So that confusion was eventually dealt with and solved, and people understood, certainly by the 1960s, what these things are and how general relativity models them. There is a central problem, though, which is still not solved, which is, you put it this way, what lies at the centre, and I'll be careful with my language, what lies at the centre of a black hole. Now just in Einstein's general theory of relativity, actually it's not right to talk about the centre of a black hole, really. So what are we picturing? It's this thing called a singularity. You might think of it as an infinitely dense point to which this massive star collapses. It's kind of the natural way to think of it. But actually, just even in pure general relativity, when you look at a nice map of a black hole, the so-called Penrose diagram named after Roger Penrose, what you see is that the singularity is not really a place in space at all. It's a moment in time. And actually, it's the end of time. So one way of picturing what's happened when a star collapses to form a black hole is that space and time are so distorted that, in a sense, their roles swap. And so what we thought of as an infinitely dense point, a place in space, at the centre of the collapse of the star, if you like, actually becomes a moment in time and the end of time, the singularity. But the nature of that thing was not and is still not understood. So that's a great mystery. And it's been long accepted that we will need a so-called quantum theory of gravity, a deeper theory of gravity, in order to explain the singularity. And for many, many years, actually, until quite recently, then people thought, well, there we are. We have a problem with the singularity. We don't really have any access to it. We don't have the conceptual tools to explore it. So it may remain a mystery for a century to come. It's not clear what to do. The great revolution in black hole research was to notice, and it began with Stephen Hawking's work in the mid-1970s, was to notice that actually there are conceptual problems at the event horizon of the black hole. Not in this extreme place, not only in this extreme place, at the singularity, whatever that might be, but at the horizon. Now that was a real challenge and extremely interesting, because we strongly expect the laws of nature that we understand now, laws of nature that we have full mathematical and conceptual control of, to apply at the event horizon. And so that's why black holes have become so interesting. It's because we have a place where we think, we assume, and indeed we're right to assume, it seems, that we have full control of the physics. We understand what's happening, but there is a fundamental clash of principle between our two basic theories of nature, general relativity and quantum mechanics. And that is ultimately why the event horizon of a black hole and black holes themselves have become so fascinating and so important. The modern revolution in our thought, which is still ongoing, by the way, in understanding black holes and quantum gravity, really does begin with work that Stephen Hawking did in the mid-1970s. Stephen Hawking, in his own words, showed that black holes ain't so black. So we've described them as prisons, in a sense. We're picturing them as a region of space from which nothing can escape. What Stephen Hawking showed in a landmark couple of papers, a tour de force of calculation actually, is that if you consider quantum theory, quantum mechanics, in the vicinity of the horizon of a black hole, then you find that they glow, they produce particles, they have a temperature. This thing that we pictured in Einstein's theory as pure geometry, as just distorted space and time, actually emits particles. It's called Hawking radiation. And one way to picture that, and Stephen in his 1974 paper gives this, he says it's a hand-wavy description. So it's not a full description, you need the mathematics for that, but he gives this hand-wavy description, which is kind of a nice way to picture what's happening. The idea is to imagine, to zoom in on space in the vicinity of the event horizon of a black hole. If you zoom in on any piece of space, the piece of space in front of your nose right now, if you could kind of zoom in and slow time down with a big microscope, you can picture what's happening as a series of particles coming in and out of existence all the time, so-called entangled particles. So it's a picture of what the vacuum of space looks like. Just to emphasize again, it's not a complete picture, it's not supposed to be precise, but it's a reasonable model of what's happening. So particles in and out of existence all the time. And that's happening everywhere, in space, everywhere that you look, in the most empty piece of space you could imagine. That's what's happening. In the vicinity of the horizon of a black hole, you can have the situation where one of those particles, those pairs of particles, is on the inside of the event horizon and one is on the outside. And then it can happen that the one on the outside, instead of merging back with its partner again, can escape into the universe. It's essentially made real by the presence of the black hole. So the other partner is interior to the black hole, and this particle heads off into the universe, removing energy from the black hole as it goes. And this rain of particles, this glow of particles, is called Hawking radiation. That has profound implications. So it's kind of a simple picture of what's happening. But the upshot is, imagine this thing. It's a black hole, it's glowing, it's just space-time geometry, but it's emitting particles, losing energy, therefore it's shrinking, which means that one day it will be gone. So black holes are not eternal prisons, they have a lifetime. One day, whatever's in there is returned to the universe. The question was, the central question that was immediately raised by those calculations is this: what happened to all the stuff that fell in? The way I've described it, the way Einstein's theory describes it, is somehow that stuff goes to the singularity, whatever that thing is, the end of time, a region of space-time that's so convoluted and distorted that we don't understand how to describe it at all. But then, one day, the whole thing is gone. All that's left in the far, far future is Hawking radiation, those particles that were produced in the vicinity of the event horizon. The question is it possible, if you could collect all that radiation, all the Hawking radiation through the whole life of the black hole, is it somehow possible, in principle, that the information about everything that fell into the black hole throughout its history is imprinted in that radiation in the far future? Is that true, or is it not true? You might say, why did I ask that question? Seems like a bit of a random question. It's a very important question. Let's say that I take anything in here, in this room, a book, the table, the camera, right? Anything at all. And I set fire to it, I incinerate it, I destroy it in any way that I can. I could throw it into a furnace, I could put it in the heart of a nuclear bomb and explode it, right? Whatever, just completely incinerate it. In physics, in basic fundamental physics, then it turns out that if you could collect every piece of that thing that I detonated or incinerated, every quantum of radiation, every photon, every particle, everything, in principle, if I could just collect it all, and I was clever enough, then I could reconstruct the thing that I had destroyed. Information is conserved in the universe, as far as we know. So every law of nature that we have says that information is conserved. The problem was that Stephen Hawking's initial calculation of the way those black holes evaporate away said that information is not conserved. Said that black holes are erasers of information. To put it very bluntly, the calculation said that once that black hole had gone, then even in principle, there is absolutely no way you could learn anything, reconstruct anything about the things that fell in, including the star that collapsed to form it. So information erasers, the only information erasers that we know of in nature. That was the initial picture of black holes as Stephen Hawking understood them back in the 1970s and 1980s. This became known as the black hole information paradox.